All right. Hello, everyone. My name is Molly McDonough. This is my submission for my final project for MATC 504, Solid State Materials. I have a little bit of a flu right now, so excuse me if I have to pause because I'm coughing or something like that. Today, I'm here to talk to you all about the history and outlook of topological materials. So to get started, I want to start off by talking about what the word topology means. So topology is the study of properties of geometric objects under continuous deformation. The layman's translation of that is essentially you can deform an object, but you can't rip it apart, you cannot tear it, but you can change the shape of it. So on the right-hand side, this is a pretty famous image, and everybody likes to use this example of turning a coffee cup into a donut. So the first phase that you see, you start off with a sphere, and then you get to that pow, and that's actually not considered a continuous deformation because you are making a hole. And so that makes a coffee cup a topologically distinct object from a sphere because it has one hole. Then you can deform a coffee cup into a donut, and those are topologically the same. And then you can further deform it into an object with 2 holes, 3 holes, etc. But the point is that things with 1 hole or 2 holes are effectively the same object. And this area of study was primarily a field of mathematics that they really had, no idea what to apply it to. Mathematicians have been studying it, but there seemed to be like no real world application for it or anything. And that was until this idea of topological materials came along. So topological materials are materials that have unique properties due to their topological order. And like crystal symmetry or magnetic order, topological order influences the properties these materials have. So topological band theory and topological materials really came about 40 or 50 years ago, thanks to these 3 guys who won the 2016 Physics Nobel Prize, David Thales, Duncan Haldane, and Michael Klosterlitz. All made significant contributions to the world of topological materials, specifically upon discoveries of the quantum Hall effect and the fractional quantum Hall effect, and explaining those Hall effects using topology. And that was really the realization of where topology came into real-world application. So as I mentioned, topological band theory and topological materials all came about because of the quantum Hall effect. So I'd be remiss if I didn't start with the original Hall effect, which of course we all know at this point. You apply a voltage to a conductor in a magnetic field, and the charges all move to one side or the other, depending on if they're electrons or holes. This is how we measure the Hall coefficient, and this came about by Edwin Hall back in the 1800s. Then about back in the 1980s, David Thales came and discovered the quantization of electron transport and used topology and the idea of topological materials to explain it. So in the quantum Hall effect, instead of basically getting a continuous resistivity reading, you have quantized basically singular resistivity readings at a particular magnetic field value. And then you also have the quantum anomalous Hall effect, which is the same idea of quantized resistivity, but it happens under no magnetic field. The quantum anomalous Hall effect is particularly interesting for its applications in electronics and in things like quantum computing, superconductivity, that kind of thing. Most 2D topological insulators are also called quantum anomalous Hall insulators, because a lot of 2D topological materials do exhibit this quantum anomalous Hall effect. What David Thales originally declared in some of his papers related to the quantum Hall effect was that the quantization, like the amount or the numerical quantization that these materials experience during the Hall effect was actually correlated to a topological number. So the amount of quantization is often called like the topological quantum number of a material. We have a whole plethora of ways to experimentally measure topological materials and determine their topological properties. I've mentioned a few already, the quantum Hall effect, the anomalous Hall effect. There's also the anomalous Nernst effect, where you apply a temperature gradient and you have a perpendicular magnetization and apply a voltage. There's also the chiral anomaly, which you have a parallel magnetic field, a parallel current, and apply a voltage. The gravitational anomaly, where you have a parallel magnetic field and a parallel temperature gradient, applying a voltage. The photogalvanic effect, topological catalysis, and then probably the most common beyond Hall effect measurements are scanning tunneling microscopy, or STM, and ARPES, which is angle resolved photoemission spectroscopy. Angle resolved photoemission spectroscopy, for those who don't know, is actually probably the primary experimental technique to actually visualize band structure of materials and actually look at it like directly in K-space. And you measure energy as a function of your wave vector and your momentum, basically. And that gives you a very high resolution image of exactly what's going on in the band structure. And nowadays you can do incredibly complex measurements, even some available at Penn State, like Nitin Samarth's group has a low temperature ARPES system, and Dr. Heikes-Bau's group has strain dependent and low temperature ARPES system. So you could apply strain and see how that modifies the band structure of the material. And at beamlines, you can do all sorts of crazy stuff like high temperature, low temperature, strain, tensile and compressive, like all different ways to modify the band structure and study how you can change the electronic properties of materials. So I don't have a ton of time to go in depth about all different kinds of topological materials. So I wanted to focus on the one that came about first. So just give a little bit of history. The 1980s is right around the time where the quantum Hall effect was discovered by David Thales. And then about 20 years later, back in 2006 or 2007, that was the first time that we experimentally realized topological insulators. First, the 2D one as mercury telluride, and then the 3D one as bismuth antimony or bismuth antimonide. And both of those materials are extremely well studied and still continue to be studied to these days because of their very interesting and unique properties. So when I think about topological materials, I start out with a baked potato. That might not make sense to you right now, but it will make sense to you in one moment. So baked potatoes, you wrap them in tin foil when you want to bake a potato to get the outside crispy, because potatoes are inherently insulators. And you wrap it in a conductor to make it crispy and make the outside conductive so you get even heating. And that's essentially what a topological insulator is. Topological insulators are materials that the bulk states are conducting, or the bulk states are insulating, and the surface states are conducting. Surface states or edge states, it really depends on what kind of material you're talking about, whether you're talking about a 2D material or a 3D material. But basically what happens in these materials is the bulk spins will all just like be doing a cyclotron orbit, and then the states along the edge will be basically jumping and skipping, making a skipping orbit like shown on the left-hand side. On the right-hand side, I show kind of an idealized band structure of a topological insulator, which still has a global gap, just like regular insulator. But you have these linearly dispersive surface states that are conducting. There are other kinds of topological materials. There's really a ton of them. These are just a few. So topological semimetals, Even within topological semimetals, there's a bunch of different ones: Will semimetals, Dirac semimetals, nodal line semimetals. There's also topological superconductors, chiral crystals. There's kind of this whole zoo of topological materials that are out there, and new ones that are still being discovered today. So why should we study topological materials? Why am I interested in this? From an engineering and like material science engineering perspective, they have a ton of applications: photonics, optoelectronics, thermoelectrics, and in particular quantum computing. There's become a lot of interest in topological materials for quantum computing, because topological materials are inherently robust to perturbations, because topology is or their topological properties are a symmetry that are inherent to the material that cannot be deformed or changed, just like crystal symmetry. And then the scientific interest reason behind studying topological materials, physicists have become interested in these materials as ways to study fundamental particles like Dirac fermions, Will fermions, Mariana fermions. There's also a lot of interesting properties of these materials that only occur in topological materials, like chiral anomalies, or like having handedness in a band structure, being able to measure the polarity of light incoming to a device, Fermi arcs, which is essentially jumping of electric field or jumping of electrical current, quantum and the quantum anomalous Hall effect, like I already mentioned, which would be incredibly useful for electronics, having that ability of quantization without having to apply a magnetic field. So just to give a brief outlook on topological materials, there's a ton of new topological materials. I want to give a shout out to this website called the Topological Materials Database. If you have time, I really recommend kind of just typing in a couple of your favorite elements and seeing if there's any possibility of a topological material there. As you can see on the left-hand side, and I've blown it up here a little bit, the database has about 40,000 materials. 6,000 of those are topological insulators, and almost 14,000 of them are topological semimetals. Most of those have not been experimentally realized, so there's a ton of ongoing challenges that are available for folks to solve, from synthesis to measurement, to studying them computationally. There's kind of this wide variety of different problems to solve in the area of topological materials, which is why it interests me so much. Another outlook piece I wanted to mention is actually one of the projects that I'm working on right now, which is realization of topological materials in group 3 and group 5 semiconductors. I call it hidden in plain sight because 3-5 semiconductors have been studied for a very long time, probably over 40 years at this point. And they've been an incredibly fruitful field of study for electronics and optoelectronics. But this group 3 with bismuth has been kind of sitting there, not really well studied. It's been tried a couple times, but there are challenges with the synthesis again. So this is what my thesis project is working on. And from the DFT calculations, aluminum bismuth, shown here, is a topological insulator, and gallium bismuth and indium bismuth are both suspected to be some kind of topological semimetal. And then, of course, I would, this couldn't be a talk about topological materials if I didn't mention Ettore Mariana and topological superconductivity. So Ettore Mariana, if you have not heard of him, you really should go look him up. He is this very strange guy who came up with this theory and then just totally disappeared 32 years later. People still don't know where he went, and he worked by himself. There's a whole backstory there. But the main idea is that in topological superconductors, there exists this Mariana fermion, which is this particle that is its own antiparticle at the zero energy point in these materials. So people have been physicists particularly have been interested in searching for topological superconductors and finding different ways to realize them to be able to study this Mariana fermion. So just a couple takeaways to kind of sum it up here. Topological materials are a really exciting and active field of research in material science and in physics. There are lots of challenges in the world of topological materials to be solved. And topological materials lend themselves to a wide variety of applications and open up all sorts of new directions for scientific study. And these are just my references. Thank you for listening. Bye.